Okay, so in this video we take a look at how we might add two vectors that are not at right angles to each other using mathematical methods instead of graphical techniques. Now, in my AP class, I showed you how we might use unit vectors to sort of organize our components. If you're in my general physics class, we can simply just add vector components using a table. I'll show you both methods in this video. A hiker walks 27 kilometers from her base camp at an angle of 35 degrees south of east. Next day, she walks 41 kilometers in the direction of 25 degrees east of north, finds a forest ranger's tower. Like to determine the magnitude and direction of her resultant displacement between the base camp and the tower. So anytime we have a vector addition problem, we always want to start with a sketch, even if we're going to do this mathematically. The sketch just allows us to make sure that we've interpreted the problem correctly. So this is her base camp. She starts out walking 27 kilometers, 35 degrees south of east. Let's use some color coding here. So I'm going to draw that as a blue vector. And again, I'm just going to approximate this. Let's label that 27 kilometers. And the angle of 35 degrees south of east is right here. Now, next day, she gets up and walks at an angle of 25 degrees east of north, so it's mostly north and a little bit east, 41 kilometers. So let's go ahead and draw that like this. Now that's 41 kilometers, and this angle is 25 degrees. Now, the 35 degrees is relative to the x-axis. I'm going to go ahead and determine this angle relative to the x-axis as well. Oftentimes we use the x-axis as our reference axis, and so it's helpful to recognize that as a 65-degree angle relative to east. Now, her final displacement is from beginning to end. Again, I'm just showing this added via the tip-to-tail method. And I'd like to find that as both a magnitude, some length, and at some angle. Okay, so we're looking for that. Now, how to do this? I'm going to break each of these two vectors into their components, and I'm going to do that over here just graphically by creating just a little diagram that looks something like this. So I'd like to find out how far that thing's projected in the east and how far that's projected into the south. So I'm choosing to show this as two sides of a parallelogram, if you will, where that would be the resultant would be the diagonal, if you will. Now let's see, 27 times the cosine of 35, and this would be negative 27 times the sine of 35. Negative because it's pointed southward, and I'm going to use the negative to denote south here. Let's go ahead and compute those. I'm getting this to be 22.1 kilometers, and this to be a negative 15.5 kilometers. Now over here, I'm going to show you in my general class versus my AP class. In my general class, I might just recognize d sub 1 as having two components here, and so let's create a little table. D sub 1 has an x component and it has a y component. And so what we found for d sub 1 is that it has two components of 22.1 kilometers in the x direction and a negative 15.5 kilometers in the y direction. Now in my AP class, I just simply write that as 22.1 I hat minus 15.5 j hat, where again I hats and j hats are just unit vectors that point either in the x or y direction, and so it's just a convenient way of organizing those components. Now for D2, let's go ahead and resolve that into its two components. Again, I'm going to use green for this one, and this one I'm going to choose to actually make a right triangle out of this. A bit easier to see for that one right here. And so for that one, let's see, the x component would be 41 cosine 65. And the y component would be 41 sine 65. And again, if I'm using my reference angle relative to the x-axis, then cosine will always get me the x, sine will always get me the y. Let's go ahead and compute those. Getting this to be 17.3 kilometers and 37.2 kilometers. Up here, I could write d sub 2, having those two components, 17.3 in the x direction and 37.2 in the y direction. And in my AP class, I might write that as 17.3 I hat plus 37.2 j hat. Now, irrespective of which way I do this, I'm still going to add the components together. So 22.1 plus 17.3 is 39.4, and this would again be for d sub r. And I'd get that as well over here, 39.4 I hat. And then 37.2 minus 15.5 is 21.7 kilometers in the y direction. And I could write that also as just plus 21.7 j hat. There we go. So two different ways of managing the addition of these vectors. Unit vector notation, just pretty convenient to do that, but we could also just use the table. Now if I wanted to determine the magnitude and direction, I would just use d sub r is equal to the square root of the sum of the squares. And 39.4 kilometers in the x direction, 21.7 kilometers in the y direction, and just compute that. Turns out to be about 45 kilometers. And if I wanted to find the angle theta, well, that would be an inverse tangent of the opposite side to the adjacent side. I'm going to go ahead and find this angle right here. So I'm going to find that angle relative to the x-axis. This is just the y component of that resultant, so that would be 21.7 kilometers. This is the x component, 39.4. And theta for that is about 29 degrees. So there we go. Two different ways for me to be able to add those. I could either write the answer in unit vector notation, or I could write it as a magnitude and a direction. Problem solved.